everyone. Welcome back from the break. So we are very happy to have Dan Kapec, and he's going to tell us about area, entanglement, entropy, and supertranslation technology.
Great. So I just wanted to thank the organizers for inviting me to give a talk here. I think it's a great workshop. I'm going to discuss some recent work done in collaboration with Andy Strominger and another student, Anna Ruclario, who's here in the audience. The title of the paper is Area, Entanglement, Entropy, and Supertranslations at Null Infinity. And it's a pretty short paper. The idea is fairly straightforward. The basic question that we want to ask is just, given some cross-sectional cut of scribe plus, which I'll call sigma, so formally we're sitting out at infinity, so the naive area of this cut, which is sort of dividing scry in half, is going to be infinite. So we would just like to know whether or not there's any nice, finite sort of renormalized area which we could hope to associate to this cut. So that's just some geometric question, can be done completely in classical general relativity. As far as I know, it hasn't been addressed before, but probably it's because it's not immediately obvious why it's an interesting question. So the main real motivation for this question is really quantum mechanical, and so it's sort of a short talk, and I don't want to spend too much time on motivation, but in both classical and quantum mechanical theories of gravitation, we have various statements which are supposed to relate entropies and areas. So probably the most familiar and least controversial one would be the generalized second law, which is just supposed to say that you take all of the areas of the horizons in the space-time and you divide it by 4, and then you add to that all of the entropy of the matter, which is outside of horizons in the space-time. That quantity is supposed to be increasing monotonically with time. So that's just some statement about how areas and entropies should evolve with time. And then there's other sorts of statements which are phrased in terms of bounds of entropies in terms of areas or entropies. I think probably the first interesting case was given by Bekenstein. And what he wanted to say was, if we have some matter system outside of a black hole with some entropy suitably defined, that entropy needs to be bounded by some order 1 number times the energy of the system times some scale which is characterizing the size of the system. So this bound was originally derived, I think, using considerations about the consistency of the generalized second law, and then there was debates about whether or not you actually needed it for the second law or not, and what should this order 1 number actually be, and how do you precisely define the entropy of the system, and lots of potentially ambiguous things in this formula. So what is your prescription for choosing the actual scale which characterizes the system? In a theory with gravitation, what do you actually mean by this local energy? So it needs to be made much more precise, but nonetheless it's some interesting conjecture which could be true in nature, and so it's interesting. And then that bound has sort of a big brother, which is due to Bousseau, which is often called the Bousseau bound or the covariant entropy bound. And that one is also fairly straightforward to state. So it just says that some entropy is less than or equal to some area divided by 4. So which entropy in which area. The prescription for the Bousseau bound is that we take some codimension 2 surface in the space-time. The area of this surface will be the area appearing in the bound. And then we look for the orthogonal null direction to this surface, which has non-positive expansion. So in this little cartoon, we sort of have these null directions, and we want to choose the one with non-positive expansion and build a null hypersurface off of this base codimension 2 surface, and that's called a light sheet. So non-positive expansion just means that as I move along this hypersurface, the cross-sectional areas are getting smaller. And then the statement of the covariant entropy conjecture is just that the entropy on this light sheet L is supposed to be bounded by the base which you built it off of. And this is supposed to be some realization of the holographic principle in gravity. And so, if you're wanting to make some hydrodynamic approximations and some reasonable assumptions on the entropy current for matter, you can actually prove statements like this in classical general relativity. So this was done in some paper by Wald, Flanagan, and Morrall quite some time ago. But of course, if you want to understand what it means quantum mechanically, you probably have to be a little bit more careful what you mean by the entropy of this quantum state localized on a null surface. Good. So the reason that I highlight these examples is because within the last couple of years, each of them has been sort of made increasingly more precise in quantum mechanical theories. So Aaron Wall has provided some nice outline for physicist proofs of the generalized second law when we incorporate quantum mechanical effects. Cassini has found a version of this Bekenstein bound, which, although it's not exactly the way that Bekenstein stated it, is nonetheless true and sort of resembles it in certain limits. And then there's been a series of recent papers by Bousseau and Maldacena and collaborators who've outlined how to demonstrate the covariant entropy bound, taking into account quantum mechanical effects. Yeah.
The Bousseau bound requires the two surface to be outer trapped or weakly outer trapped. Is there a condition on the inner nulls?
Well, the Bousseau bound is just a construction for a particular type of null surface, right? So it's one where I explicitly choose the null direction to build it, which has
Which is one direction.
So that's So you can choose basically in this picture either this one or this one, but if you try to choose this one, you're immediately going to run into issues, right? So as far as I know, this one, so it's sort of a limited bound. It's some compromise between being true and being general. But as far as I know, it avoids any of the obvious counterexamples in cosmological settings or sort of tricky counterexamples which people have tried to come up with. And so recently, people have sort of begun to make sense of what this formula should mean quantum mechanically as well. Any other questions? Great. All of these recent advances in this area make use of one particular quantity, basically to make precise the left-hand sides of these inequalities, and also what does it mean by the entropy of a matter system outside of a black hole quantum mechanically. And that quantity is called entanglement entropy. Okay, so entanglement entropy is more or less a quantity which measures correlations between different parts of quantum mechanical systems. So if you had a system which was just on a line, it could be some set of spins or something more fancy. The quantum state on the line would just be described by some density matrix rho, which, if it's a pure state, has a very simple form like that. So pure state just means that it has no von Neumann entropy. So trace rho log rho is 0. So then the question you would like to ask is, if I divide this system in two, for instance, and I separate it into some subsystems A and B, and they have some associated Hilbert space factors HA and HB, you would like to know, to what extent is one part of this system correlated with the other one. So to answer that question, you calculate what's called a reduced density matrix, which is basically just a partial trace over the factor of the Hilbert space, which you want to forget about. So in other words, if I want to calculate the reduced density matrix for the left-hand side subsystem, I just do a partial trace over the Hilbert space associated to the right-hand side of the system, and that gives me this reduced density matrix rho A. And then the entanglement entropy is just the von Neumann entropy of this reduced density matrix. So I just take negative of trace rho A log rho A, and if that is non-zero, it means that this part of the system had non-trivial correlations with the other part of the system. And that's what's called the entanglement entropy. Okay. Are there any questions just about the basic definitions?
So it's only defined for pure state? But if the original state was a pure state?
Strictly speaking, it's not really an entanglement entropy. If you started with a mixed state, you can still calculate it, but then it's also going to be telling you about the sort of coarse-grained thermodynamic entropy, which was already present in the state. So it's not as interesting as it is.
If it's a mixed state, you can always extend the inverse.
Yeah, I think you can purify it. But okay, it's not really important. Okay, so that's something which makes sense for systems with finite dimensional Hilbert space. It's very useful in quantum information. But of course, if we move to continuum quantum field theory, like everything else, it's going to be formally infinite. So it's infinite, but it's infinite in a very sort of controlled geometric way. So in particular, if you calculate the entanglement entropy in a quantum field theory, you'll naively get an infinite answer. If you then put in some UV regulator to try and make the theory finite, what you will find is that the leading divergences, they're all geometric, and they're written in terms of the geometry of the entangling surface itself. So the leading divergence will be something like the area of the entangling surface by the cutoff squared, and then there'll be subleading terms as well. So that's not really surprising in quantum field theory, because like almost all of the other divergences that one encounters is because of high energy, short distance, ultraviolet modes. So the basic physical picture is just that, if you don't have any UV cutoff in the theory, there's sort of infinitely many of these short range modes on both sides of the entangling surface which are correlated with each other, and that's why all of these divergences are sort of localized to the entangling surface. So that's no good. We don't really have any use for infinite quantities, but it's also not a very interesting divergence because it's something which is going to be true in any state. So it doesn't really matter what state I'm evaluating the entanglement entropy in. I'm always going to have these geometric divergences. So typically what people do to get a finite and useful quantity from this is to do a vacuum subtraction. So these geometric divergences, they're also present for vacuum entanglement. So in order to get a finite number, people will take the entanglement entropy of some state which they're interested in and then subtract from it the entanglement entropy of the vacuum, and that gives you some finite number which you can use to characterize the entanglement of the state. So I want to say, first of all, that I think we have some issue with that procedure when we have gravity in asymptotically flat space-time, precisely because, as Prahar was discussing earlier, we have basically a huge degeneracy of vacua in asymptotically flat spacetimes, which are basically the different BMS vacua. So they all sort of supertranslations of one another. They have zero energy, but for instance, they have different angular momenta. And so it's not obvious that doing this naive vacuum subtraction will give you the same thing in each BMS vacuum. So I'll say a little bit more about that later. Another thing is that, so this entanglement entropy, which plays a very important role in all of these entropy bounds, it relies very much on having some well-defined surface on which the Hilbert space of the theory factorizes into two different pieces and some background space-time. But if we have very strong gravitational fluctuations in a quantum mechanical setting, the geometry is fluctuating all over the place. It's not really clear what you mean, or that you'll be able to define it in the bulk of the space-time. So that's some problem which you might be worried about. Fortunately, there is a part of an asymptotically flat space-time which is sort of under control and doesn't have huge fluctuations in the geometry, and that's just null infinity out here, where everything has sort of, the theory has more or less linearized itself for you. Everything has become very dilute and weakly interacting, and you might still hope to be able to make some sense of entangling surfaces and entanglement entropy, and avoid the sort of difficulties that you could have when crazy stuff is going on in the interior of the space-time. So that's sort of why we're going to study this question at null infinity. So, for instance, the Busso bound, the recent proofs which have been given, they sort of rely on some very weak gravity approximation, and it's not clear that that will really be useful in the generic setting. But that's fine that we have to pose the problem as Scry, because Scry is also sort of, I think, the natural place to discuss the information puzzle in asymptotically flat spacetimes. So one would like to have some diagnostic for information loss, which you can pose only at the boundary of the spacetime, so that you never have to go in the bulk where you don't necessarily know what's going on. So the analog would be, or the analogy would be, an anti-de Sitter space where the information puzzle is a little bit different, but nobody thinks you have to worry about information loss there because we found a way to pose the problem at the boundary of the space-time where everything is sort of under control, and you know that there's a dual description in terms of a unitary conformal field theory where there won't be any information loss. So we'd like to have some similar question which we can pose simply at the boundary of asymptotically flat spacetimes, which would be a measure of whether or not, for instance, black hole formation and evaporation was a unitary process or not, because inside of the bulk, it's still a very confusing question, even in anti-de Sitter, where we have very powerful tools which let us answer lots of questions which we can't even in asymptotically flat spacetime. So the basic diagnostic for information loss in the information puzzle is that you start with some state on Scry minus, which you assume to be pure, and then it's going to evolve to some state on Scry plus, and the question is just whether or not this state rho out, is it pure or not? So is trace rho out log rho out equal to 0. Okay? So that's sort of the, if you can answer that question, you more or less solve the information paradox. So could hope to even calculate something which is a bit more refined, and that would be to take the state on scribe plus and calculate the entanglement entropy of the state across some cut of scribe. And then that's going to define for you some curve along scribe, more or less parameterized by the retarded time, which is going to basically keep track for you of the correlations in the early and late Hawking radiation. So I think if you asked most people what would be their naive expectations for unitary formation and evaporation, they would tell you, well, early on, Scry doesn't know anything about the black hole or that it's evaporating, so this should probably start out at 0, and then starts to find out about the black hole and thermal radiation, and the curve grows for a while, and then somewhere around the page time, it needs to start coming back down because we get information back and correlations between the early and late Hawking radiation, and it had better go back down to 0 at the end when we trace out all of Scry, because then we're just calculating the von Neumann entropy of the entire state, and that had better be 0 if it's a pure state. So I think that would normally be the naive expectation for an answer to a question which you can pose purely at scribe plus. But as I said before, this issue with, so this obviously is not what you will get if you just do the naive calculation, because as I've said in continuum quantum field theory, this quantity will just be infinite. So this has to begin with to be some subtracted version of the entanglement entropy of the state. And if it is, generically in scattering processes in asymptotically flat spacetime, the BMS vacuum which you start out with is not the same as the BMS vacuum which you end up in. So it's not clear whether or not you can actually make this curve go to 0 at both ends of Scry plus and Scry minus. If I do the vacuum subtraction with respect to the future vacuum, I could make it go down to 0 here, but it's not obvious that I can also make it go down to 0 at the other end of Scry. So we would like to just begin to try to find some concrete, well-posed calculation which we can do at Scry plus, which would be a diagnostic for the information loss. This is obviously a difficult quantity to compute, so it would be useful if we could use some of these nice bounds on entropies which have been derived and discussed recently, push them out to Scry plus and use them to sort of see if we can force this curve down to 0 in different directions, or at least bound it, say something non-trivial about the curve. But we can't simply take the Bousseau bound, which has been proven for finite light sheets inside of the bulk, and yank it out to infinity, because if we do that, the area of the base will become infinite and it's just trivially satisfied. So we're going to be bounding something by infinity, and that's really not that useful. It's going to be satisfied in a trivial way. So what we wanted to do was to see just whether or not we can find some renormalized area for cuts of Scry plus, which has nice properties and makes sense, and then hopefully later on we can see if we can sort of use this to constrain this function and say something interesting about the information puzzle. So are there any questions about that? Okay, so the geometric setup which I want to consider is just asymptotically flat spacetimes, and I'll put the metric in Bondi gauge. So near Scry plus at leading order, the metric is going to look like this. This is just the metric for flat space in these coordinates, and then of course we will have subleading directions. Okay, so this MB is the Bondi mass aspect. It depends on U, Z, and Z over the 2-sphere at infinity at that retarded time. CZZ is more or less the shear on the sphere. We use it to define what's usually called the Bondi news tensor. The Bondi news is just basically a diagnostic for whether gravitational radiation is bringing energy out through scribe plus. So if it is identically 0, then there's no energy flux due to gravitational waves through scribe. So this gamma ZZ bar is just round metric on the sphere, and his associated covariant derivative is dz. Good. So let me make a little bit of notation just to be able to express things succinctly. So there's sort of a natural energy which you can associate to the gravitational waves passing through scribe, which is more or less just the square of the Bondi news tensor. It's natural because this is the object which appears in the Bondi mass loss formula, which governs the time dependence of the mass aspect. And then I'll also want to define a 2 form, which is more or less the divergence of this tensor C, and another one which is basically the same but for the news. And I want to call the volume form on the sphere epsilon. Okay, so so the leading order constraint equation in these coordinates near scribe plus can be written in the following form. And what this formula basically says is just that the mass aspect, which characterizes the energy in the system, is monotonically decreasing as you move along scribe plus. So we have this object here, which is basically a square of something, so it's a positive number. So this is sort of the energy carried away by gravitational waves. This term here is, if you unpack it, is just the total derivative. In sort of more recent language, you would call this soft graviton contribution. So it will integrate to 0 if you integrate the mass aspect over the sphere and just ask what is the total energy of the system at a particular value of retarded time. But if you want to look at the mass aspect as a function also of its angles, what this term is doing is really shifting around local energy on the sphere, but integrating to 0. So in that sense, it's a soft piece, no total energy, but it does sort of give you local energy in different directions. So this is the piece which is sort of showing up in the soft theorems, which Prahar was discussing.
What is it? Ipsil or
Sorry?
Ipsil?
Yeah, sorry. So this is dz. Any other questions? So I want to, I want to impose one other boundary condition just for simplicity, and also because I sort of have in mind the information puzzle. So I want to ask for spacetimes which revert to the vacuum in the far future. So after some finite retarded time, the mass aspect turns off, and the sort of shear on the sphere becomes basically what I would remind you what that means and why. So naively, you might have said just that the vacuum should be C equals to 0, but BMS sort of told us quite a while ago that that's not the only thing which you can have. So the BMS group, which is the asymptotic symmetry group for asymptotically flat spacetimes, basically involves two pieces, one of which is the normal Lorentz transformations, which are just realized as conformal transformations on the asymptotic sphere, and the other is the supertranslations. And the supertranslations were the real surprise when this analysis was first done. I think people spent quite a while trying to get rid of them because they thought, at large distances and low curvature, general relativity should in some sense reduce to special relativity, but it seems that that's just not the case, at least near null infinity. So these supertranslations they're more or less generated by vector fields which asymptotically are labeled by a single function on the sphere. And they have subleading pieces. Okay, and then what they're doing is basically more or less just moving you by different amounts along stride depending on where you sit on the asymptotic sphere. And so if you just work out, and these formulas are known since the 1960s, how do these things act on the asymptotic data? Well, they act just as you would expect with things like the news and the energy momentum tensor. But there's a little bit of a surprise for the tensor CZZ. So it has a piece which so as promised, that's divergent in the large R limit. And so we want some prescription to make it finite. And I'm not claiming that this is the only prescription or not. This is just some attempt, the first swipe. So what we want to do is to define some fiducial vacuum geometry. Okay, and this is sort of motivated because this is the sort of thing that people are doing when they try to make the entanglement entropy finite. You calculate it in the state that you're interested in, it's infinite, and we subtract from that something which is calculated in the vacuum to get a finite answer. So we'll take this geometry to be the one which is flat and is basically just a super translation of flat space. And the particular super translation that I do is just by the super translation vacuum that this state, this geometry settles into in the far future. Okay? I'm going to do that vacuum subtraction. And so the notation is going to be AF sigma, the area of this cut in this geometry which I'm interested in, and I subtract from that the area of this surface which is vacuum and is just defined by this super translation of flat space. So if you do that calculation and then you use the fact that, so this is the u at a cut and then Cf is the u at infinity, you can actually rewrite this in terms of an integral over the future of the cut of scry, and it has the following form. Okay, remember that this V is more or less the divergence of the news tensor. This integral, as I said, is taken over the future of the cut of scry, which means my cut is here, the integral is done on this part of the hypersurface. And then, so something which is nice, but maybe not completely surprising, is that if you use the Einstein equations at leading order and do some integration by parts, you can actually rewrite this in a very suggestive form. Again, as an integral to the future of the cut. Yeah, so it's interesting for a couple of reasons. The first of which is that this is formally very does it, which extends it and ends on these two endpoints. And of course,